I want to look at some free body diagrams. And so here I have a picture of some sort of ball and a stick resting on the ball, and both are on the ground. Nothing is moving in this example, and I want to evaluate the forces and therefore draw a free body diagram here for the ball. So before I get into that, I want to first analyze what are the forces on the ball. And so if I sort of look at the ball, I want to see everything in contact with the ball. I might draw a line around it. Of course, there's gravity, is a long-range force that acts on the ball, and anything else has to be in physical contact with the ball. And so we have what looks like the ground. The ground is in contact with the ball, and so there is a contact force that I might break into a normal force and a frictional force due to the ground. And there's also then this stick that's resting on the ball at some angle theta here relative to the ground. And now it is also going to exert contact force on the ball. And I think I might want to break this contact force into a normal force and a frictional force, which I know, given our models of the contact force, is perpendicular and parallel to the surface of contact between the two objects. Well, what does that mean? So, this surface looks like it's going to be along the plane of the stick here, and so that's at an angle theta relative to the ground. So I think that plane is also important. So if I go over here and I'm going to draw a free body diagram, of course I represent my object here with a dot. One thing that a free body diagram always needs is a coordinate system. And in this one, I really have two sets of axes that I'm interested in, and one at an angle theta relative to each other. When I personally have that situation, the first thing I do is I get those coordinate systems on my diagram. Not necessarily coordinate system, those two sets of axes. So I get an axis that's parallel and perpendicular to the ground, and then I create another set of axes that's at the same angle theta that's relevant in my problem. Given my visualization of the problem, I anticipate that these two sets of axes are important, so I get them right away on my paper. Now I have an easy way to guide my eye when I draw my forces on my free body diagram. Okay, so let's first start with gravity. So I know gravity points vertically down, and so I'll draw that vector, and I'll give it a label. F sub g is my force due to gravity. Okay, so it's pointing straight down. And so now I need to evaluate my contact forces. Well, first let's look at the ground on the ball. So it's a contact force. It can be broken into a normal force and a frictional force. The normal force is perpendicular to the surface, so I look at my picture, where's the surface, and it acts in the direction of the object. So my agent is the ground, my object is the ball, so the normal force points up, and I'll give that a name. I might call normal force of the ground on the ball. So I have N for normal, and I get some subscripts so I can identify what that force is. So there's also a frictional force that then is tangential to the surface or perpendicular to my normal force. So what direction does that point? Well, since nothing's moving, it's a static frictional force, and the static frictional force points in the direction opposite that which the object would move if there were no friction. So that brings us back to the picture. Imagine there was no friction between the ground and the ball. What would happen? Well, because the stick is pushing on the ball would slide to the right if there were no friction between the ground and the ball. So that means the frictional force between the ground and the ball has to point in the opposite direction, still parallel to the surface of contact between the two. So the frictional force, which I'm going to call frictional force, I'll also call that F, ground on the ball. So you'll see what I've done here. I have sort of, for my notation, I have ground on the ball, G and B subscripts to identify the two parts of the frictional force. I have F for friction, which is the same sort of my force due to gravity here, but the subscript G reminds me that that's due to gravity. My subscripts here tell me that this is the ground on the ball. There's no magic notation here other than you want to use notation such that when you see your notation, you know the physical effect, physical force, physical entity that notation represents. Okay, so now we have those two forces, which are the two components of the contact force of the ground on the ball. All right, so now let's take a look at the contact force of the stick on the ball. Okay, so there's a normal force and a frictional force. The normal force is going to act perpendicular to the surface, which we identify as sort of the surface of the stick, and it points in the direction of the object. The object is the ball, the agent is the stick, and so that's going to point along this axis. So you see the convenient having this set of axes tilted at an angle here, and so now I can just lie this vector along that axis because I know it's perpendicular to the axis of the stick. And I don't worry too much if the angles aren't exactly representative. I know that this angle here is equal to the angle in my picture. Okay, so now I need a frictional force of the stick on the ball. Okay, so that's parallel to the surface of the contact, but in what direction? Well, so we have to determine if there were no friction between the stick and the ball, what would happen? Well, you would slide on this surface. This surface would slide, and so again, what you would get is you would get the ball rolling to the right and then sliding on this surface between the stick and the ball. So what does that mean? Well, so we have to think about the motion of the object relative to the agent. And so this surface, the point on the surface of contact between these two objects, is sliding that direction as the ball is rolling away. And so that means the force of static friction had to point in the opposite direction, which would be along the plane of contact, which would be in this direction, down the slope. So that means that the frictional force of the ball on the stick points in that direction. I have the normal force of the ball on the stick here, and now I have a free body diagram for all 5 of my relevant forces, and all at the correct angle relative to each other. And now I can decide which coordinate system is my plus my x and y coordinate system. It could be the one perpendicular and parallel to the Earth, or it could be the tilted axis, whichever one I think might most conveniently solve my problem. But I already have the forces at the right angles relative to each other, so the rest is just finding the components on the appropriate axes.